Hello everyone and welcome. Today we're going to peel back the label on your favorite fizzy drink. We're going to get into the really incredible, kind of hidden science that keeps a bottle of orange soda from, well, turning into a separated, unappetizing mess. So let's just dive right in and uncover the clever chemistry going on inside.
I mean, have you ever really stopped to think about it? You've got a drink that's mostly water, but its flavor comes from orange oil. And what's the one thing we all learned back in school science class? Yep, oil and water do not mix. So how does that bottle on the shelf stay perfectly blended for months or even years at a time?
Well, the answer starts with understanding this fundamental conflict that's happening inside the bottle. It's really a battle of basic chemistry. It's a story of two ingredients that, let's be honest, just do not want to stay together.
So on one side, you have that delicious citrus flavor that comes from essential oils. And these oils, of course, are not water-soluble. They're also less dense than water. Then, on the other side, you have the main part of the drink, sugar water. It's water-based, and because of all that sugar, it is much, much denser. So, what happens when you just leave them alone? Well, you guessed it. The lighter oil is always going to try to float to the top, creating exactly the kind of separation we're trying to avoid.
To solve this whole problem, food scientists have to create something called an emulsion. Now, an emulsion is just a fancy word for a mixture of two liquids that normally wouldn't mix. So your soda isn't just a simple mix. It's this carefully constructed emulsion, a really delicate balancing act that's been engineered to keep the oil and water playing nice.
But, just creating an emulsion is only half the battle. The real challenge is that all emulsions are, by their very nature, unstable. Physics is constantly trying to pull them apart. Let's take a look at the forces that are working to break it all down.
You see, an emulsion doesn't just fail in one simple way. It can break down through this whole three-step process. And food scientists have to guard against every single one of these steps to make sure your drink has a nice, long, stable shelf life.
Okay, so it all starts with step one, creaming. This is where the less dense oil droplets slowly start to rise to the top and form a separate layer. This is followed by step two, flocculation. This is where all those little droplets start to kind of hold hands and form little clumps. And these clumps, they rise way faster, which just speeds up the creaming. And then you have the final blow, step three, coalescence. The droplets don't just clump anymore, they actually merge together, forming bigger and bigger oil slicks until, poof, the emulsion is completely broken.
So the really crucial thing to get here is that scientists are in a constant fight against the laws of physics. They're literally trying to stop a natural process of separation that is pretty much inevitable.
And this right here, this is the law they're up against. It's called Stokes' law. Now, you do not need to memorize the formula, don't worry, but what it tells us is actually very simple. It calculates the speed at which a little sphere, like our oil droplet, is going to rise or fall through a liquid. The formula basically looks at the size of the droplet, its density, and the density of the water around it. And the only way to stop this separation is to somehow play with these variables and get them on our side.
Now, what's really interesting here are the numbers. The orange oil has a density of about 0.845 grams per milliliter, while the sugar water is all the way up at around 1.04. Now, that gap might seem pretty small, but according to Stokes' law, it is a huge difference. It's more than enough to cause that separation to happen fast. So the main goal becomes, somehow, to balance these scales.
So the first idea to solve this is pretty logical. Just add something heavy to the oil. These things are called weighting agents, like ester gum. You just dissolve them in the oil, and boom, the oil's overall density goes up. But there's a catch. The use of these things is heavily regulated for safety reasons, and the amounts you're allowed to use just aren't enough to make the oil as dense as the sugar water. So it helps, for sure, but it doesn't solve the problem completely.
So if you can't make the oil heavy enough, what do? Well, this is where scientists came up with a much more elegant solution. Instead of trying to fight physics, they found a really clever way to actually use it.
You see, the secret isn't about just mixing the ingredients together harder. No, it's about building a microscopic structure around every single tiny droplet of flavor oil. It's like a tiny invisible suit of armor.
This diagram here shows exactly how it works. Scientists add a substance, something like gum arabic, to the water. And this special ingredient, it forms a very thin but dense film around each little oil droplet. This film acts like a shell, and it adds just enough extra weight to make these tiny droplets neutrally buoyant. And that just means they don't sink and they don't float. They just hang there.
This really clever process actually has a name.
It's called microencapsulation. We are essentially creating billions and billions of these tiny microscopic capsules, and each one is holding a little bit of orange oil just perfectly suspended in the sugar water. It's amazing.
And this is where it gets truly mind-blowing. This isn't just a diagram. These are actual microscope images that prove the film is real. Okay, so on the left, you see a normal oil droplet. But on the right, get this, a scientist used a teeny tiny syringe to pull the oil out of the droplet. And what's left behind? The wrinkled, empty shell of gum arabic, kind of like a collapsed balloon. This is physical proof of that microcapsule.
And just look at the strength of this film. In this picture, an aged oil droplet was pushed out into the solution, and that gum arabic sheath is so strong that it forces the oil into this weird sausage-like shape. It's preventing it from going back to its preferred state, which is a perfect sphere. So this film isn't just adding weight, it's a strong protective barrier that both balances the droplet and stops it from merging with others.
So, with this microencapsulation technique, we're moving from just a theory to a practical, engineered product, something that can actually sit on a shelf for months and stay perfect.
And here it is, the ultimate proof that it works. These charts show the size of the oil droplets. You can think of the peak of that curve as the most common droplet size. The chart on the left shows the sizes in a drink that's just 2 days old. The one on the right is the exact same drink 6 months later. Look at that. The shape of the curve is almost identical. That means the droplets haven't merged or grown at all. It's incredible.
Now, okay, there is a minuscule change in the average droplet size. We're talking nanometers here. But the practical result is a perfectly stable drink. The amount of visible separation you'd see in the bottle over its entire shelf life is basically zero. In short, the emulsion holds. The science works perfectly.
So let's just sum it all up. This invisible film of gum arabic is doing 2 critical jobs. First, it adds just enough weight to the oil droplets to cancel out their natural urge to float. And second, it acts as a physical barrier, stopping the droplets from touching and merging. And the result of all that? The stable, perfectly mixed, and pleasantly cloudy soft drink we all know and love.
So, the next time you pop open a bottle of soda, maybe you'll see it a little differently. It really makes you wonder, doesn't it? What other amazing, invisible science is secretly at work in the food you eat every single day?